Welcome back. We're going to continue talking about some basic trig ratios. We're going to do two more examples. Here, we're going to start with cosine alpha being 12 over 13. And we're going to show that secant alpha equals 13 over 12 using definitions. So I want to show this is truth. So I'm going to start with secant alpha and try to use my definitions to create 13/12. I want to verify that this is a true statement or prove this is a true statement. So I'm going to start with secant alpha and I'm going to turn it in to 13/12 given what I know. Well, secant alpha we know is reciprocal to 1 over cosine alpha. And we were given a cosine alpha value. It's 12/13. So this is equal to 1 over 12/13. And if we know anything from algebra, division by a fraction is multiplication by the reciprocal. So this is 1 times 13 over 12 or 13/12. Therefore, we proved this was a true statement. Let's try that one more time. We'll say, given tangent theta equals 2/3, let's find cotangent theta. So cotangent theta, by definition, we know that cotangent theta is equal to 1 over tangent theta because it's reciprocal. So that is 1 over 2/3 because tangent theta is equal to 2/3. And 1 divided by 2/3 is 3/2. So cotangent theta is equal to 3/2. And that should make sense because tangent and cotangent are reciprocals. 2/3 and 3/2 are reciprocals. Now we're going to talk about similar triangles and how they relate to each other. So one thing we know is that if two triangles have corresponding angles which have the same measure, they can be called similar triangles. And what that means for us and how that's useful to us is that the lengths of the corresponding sides are also in the same ratio. So, for example, you can see I have these two triangles and they look like all of those angles are exactly the same. And if we were in class, I'd pick them up and I'd match that little triangle's angles up into the three angles of the larger triangle, and you'd see that, but I can't do that in my notes app here. But I'm going to draw this for you. I'm going to call this larger triangle. I'm going to label it with angle alpha, 2 arcs, angle beta, and similarly on my little triangle, I'm still going to have alpha and beta. Both of these triangles have a right angle in the corner. So what we can see here, maybe the sides on the larger triangle are 9, 12, and 15. Since we know that the corresponding angles have the same measure, the top ones are both alpha, these lower right ones are both beta, we might be able to say that 9 could become a 3. It'd be 1/3. And if the 9 became a 3, 15 divided by 3 would become 5. 12 divided by 3 would become 4. So these are two similar triangles, and all of the sides, the corresponding sides, are in the same ratio. And we can prove this. Suppose I wrote cosine of beta for each triangle. So cosine of beta on this large triangle, beta, and cosine is adjacent over hypotenuse. Adjacent to beta, the side touching beta is 12. The hypotenuse is 15. So cosine beta equals 12 over 15. And if we reduce that fraction, we would say that cosine beta, dividing both by 3, gives us 4/5. On my little triangle, if I look at beta here and I say adjacent over hypotenuse, again, I'll get that cosine beta equals 4/5. And you can see that those are the same ratios. So that's just more proof that these similar triangles are always going to have this same ratio. All right, let's look at an example. Here we are given cosine theta equals 0.7, and we want to find cotangent theta. All right, we have a lot to think about here. One thing, we always think about these trig identities as being ratios, and cosine theta being 0.7, that's not a ratio. Well, we can write 0.7 as a fraction or a ratio. 0.7 written as a fraction is the same as 7/10. So cosine theta is equal to 7 over 10. All right, let's draw a right triangle in here. Where should I put theta? Theta just represents an acute angle. I can put theta at the top. I can put theta at the bottom. I bet most of you want to draw it at the bottom, so I'm going to draw it at the top. So there's my theta. Let's think about what we know regarding cosine. We might come over here on the side of our page and write SOHCAHTOA, SOHCAHTOA. Some old hippie caught another hippie tripping on acid. So we know that cosine is adjacent over hypotenuse. So 7 is adjacent, 10 represents my hypotenuse. Well, my hypotenuse is this long side here opposite the 90-degree angle. But which of these two legs is adjacent to theta? And adjacent means beside or touching, as opposed to opposite, not touching. So this vertical side is adjacent, so I know that's going to be 7. So that is adjacent theta, and this guy is my hypotenuse. Now, we're being asked to find cotangent. Cotangent's reciprocal to tangent, and tangent I know because I've stored it. Tangent theta is opposite over adjacent. That means cotangent theta is adjacent over opposite, right? Because those are the reciprocal for each other. So we're still looking at theta. I know my adjacent side, but I need my opposite side. How am I going to find that opposite side? We can find the opposite side. If we're missing a side on a right triangle, we can talk about using the Pythagorean theorem. And so by the Pythagorean theorem, if I come over here to find my opposite side, I would say, I'll just call this x. X squared plus 7 squared equals 10 squared, which is 100, which is x squared plus 49 equals 100. X squared equals 51, or rather this opposite side, x, is going to equal the square root of 51. Now, algebraically, when we use that square root to solve, we're supposed to write plus or minus, but this is a side length. It's not a negative measure, so it's always going to be that positive value. Therefore, cotangent theta, now that we know this, cotangent theta, so theta, adjacent over opposite, that's going to be 7 over the square root of 51. Technically, We should rationalize this. Cotangent theta is going to equal 7 root 51 over 51. Now, rationalizing is something you should know how to do. We want to get that radical out of the denominator. So I multiply by 1 and I form that 1 by looking at what I have here in my denominator. So root 51 times root 51, that's root 51 squared, and they cancel each other. So I have a 51 in the denominator, and I have 7 root 51 in my numerator. So that's my final answer here. So I hope that gives you a better understanding of how we like to use our trig identities. We remember SOHCAHTOA, and we identify our opposite and adjacent sides based off of the acute angle we are considering. And it could be anywhere in the triangle. If I had drawn this picture and I'd put theta down there, I would have just drawn it to have this side 7, and I would have calculated this one to be root 51. It would still work out exactly the same way. So you're always saying, where is that acute angle? And then what are my opposite and adjacent sides in relation to that important acute angle? All right, I'm going to stop this video and we'll continue moving forward in the next.